So in our previous chapter, we covered many kinds of graphical summaries of data. Now we're going to talk about numerical summaries of data. Just one number or a couple of numbers that kind of summarize a data set for us. First of all, let's talk about measures of center. The most common numerical summary of data is to find the data's center or average, but that can be done in a couple ways. The mean of a data set is the sum of all the data divided by the numbers of the mean of a data set is the sum of all the data divided by the number of numbers in the data set. This notation with the Greek letter sigma is pretty common for indicating a summation. And the notation x subscript I, meaning that the numbers in your data set are referred to as x subscript 1, x subscript 2, x subscript 3, and so on. And there's also different notation, whether we're talking about a sample mean or a population mean. For a sample mean, this notation is referred to as x bar. For a population mean, this notation is referred to as mu. The operation is the same either way. We're adding up all the numbers and dividing by how many numbers there are. But also notice that for a sample, the number of numbers is a lowercase n, and for a population, the number of numbers is an uppercase n. Anyways, we have different, even though it's the same operation, we have different notations because later on in the course, there will be times when we're referring to the population mean and a sample mean at the same time. So we need to be able to keep those two straight. Normally, the first time I put a set of numbers on the board in class and I ask students what I should do with these numbers, almost always the first thing they say is add them all up and divide by how many there are. So that's exactly what the mean is. So for example, if we're going to find the mean of this data set, we're going to use this data set over and over again during this lecture. We simply add all the numbers together and divide by how many numbers there are. Another important measure of center is the median, which is the actual center of the data. So to find the median, you usually have to have the numbers in order. And in this case, there's an even number of numbers, so the median will land in between two of those numbers. Like right in here, 4 below this point and 4 above this point. So the median is actually in between the number 14 and the number 16. So the number that's in between 14 and 16 is 15, which you can easily find by adding the numbers together and dividing by 2. Most books don't have a symbol for median, so they just refer to it as median or sometimes MED. If the data set has an odd number of numbers, then the median, instead of landing in between two of the numbers, the median will actually be one of the numbers. So in this case, with 9 numbers, the number 92 is actually in the center, and there's 4 numbers below it and 4 numbers above it. Okay, so sometimes the median is one of the numbers and sometimes it lands in between 2 of the numbers. So mean and median are both measures of center, but they're rarely equal to the same number. The mean can be greatly affected by unusual observations or outliers, which we'll learn the exact definition of outliers in a little bit, and also affected by skewness, but the median is not. So the median is said to be a resistant measure of center or resistant to outliers. So remember this discussion from previous notes about the 3 different types of skew. When a data set is skewed or has outliers, it's best to use the median to describe the center. As this course goes on, we're going to use the mean way more than we'll use the median. But just a good thing to know that median is what should be used when the data is skewed. Later on in this course, we're going to be dealing with a lot of distributions that are roughly symmetric, which is why we get to use the mean. I wanted to show you an example of this with some actual data. I have on my calculator this list here, which is the players' salaries for the LA Dodgers. Okay, and if I do a histogram of that data, you will notice that the data is very skewed. Like a lot of data involving money, the data is going to be very badly skewed. So we have this really tall bar, histogram bar, a big pileup of money near zero, and then this tail going all the way out here. And for the Dodgers' salaries, this bar that I say is piled up near zero is from a $500,000 to 5.8 million. So for most of us, 5.8 million is not near zero, but 5.8 million is near zero when you compare it to 37 million. So a lot of times data involving money ends up like this, really badly skewed to the right, because even with normal people's salaries, there's a whole bunch of people that make between 0 and 100,000, and then there's less that make between 100 and 200,000, and then even less that make between 200,000 and 300,000, and so on. So I might have shown you this picture of the Dodger salaries before, but now what I want to do is show you the difference between the mean and the median, and why the mean is not a good idea here. The mean salary for the Dodgers is 5.8 million, but the median salary is only 1.6 million. So there's a huge difference between the median at 1.6 and the mean at 5.8 because of how severely skewed the Dodger distribution is. As a matter of fact, if I was to look at the Dodger salaries, give me just a second here. If I was to look at the Dodgers salaries, there's a whole bunch of players making around $500,000 because that's the Major League Baseball minimum. And I've got to go quite a ways down the list before I get to people making $1 million. So I've got about 20 people making under $1 million. I've got 22 people making under $2 million. And then the salaries kind of rapidly start to rise. And I eventually get up to 30 something million, which a couple players on the Dodgers are making. So the average Dodgers salary, the mean is 5.8 million, but the 5.8 million is not a good description of the typical Dodger salary because over half of the Dodgers make less than 2 million. So the median, which is 1.8 million, is a much better description of center. And I was talking about that this happens with most things involving money. If I just look up average home price in LA County, the quote unquote average home price, notice I use the word average, they are almost always going to report this as the median home price, because median is a better measure of center than mean is when the data is skewed to the right. Okay, So not only when it's skewed, you should use the median, but also a good thing to remember is when it's perfectly symmetric, the mean will equal the median. When the distribution is skewed to the right, the mean will be greater than the median. And if it's skewed to the left, the mean will be less than the median. Okay, so that's it for measures of center. The book also talks about the mode as a measure of center, but we're not going to talk about that. That's a little bit elementary schoolish. Now we're moving on to measures of position. So there are positions within the data that are nice to know about rather than just knowing where the center is. For example, it would be nice to know where the 90% mark is in the data. Like, where do you have to be in the data set to have 90% of the data less than that location? So first up, and all of these measures of position or location tend to end with the word aisles. So first of all, the quartiles. For most of the planet, this is the way we do quartiles. The quartiles, as the name implies, like quarter, as best as we can, divides the data into 4 pieces, which is not too hard to do when there's 8 numbers. The median has already separated the data into a lower half and an upper half, and all we have to do is find the median of both halves. So the median of the bottom half is referred to as Quartile One, or Q1, and the median of the upper half is referred to as Quartile 3 or Q3. And I'm finding this 21 the same way I found the 15, adding the 14 and the 16 together, divide by 2. Add the 19 and the 23 together, divide by 2. Add the 11 and the 12 together, divide by 2. You have to do that little operation whenever this lands in between 2 numbers in the data set. And these are sometimes called Quartile 1 and Quartile 3. Sometimes they're also referred to as the upper quartile, lower quartile. And then there's 2 other important numbers in the data set, which would be the minimum at 10 and the maximum at 29. And that would give us a total of 5 numbers, which statisticians often refer to as the 5-number summary: minimum, Quartile 1, median, Quartile 3, maximum. So any kind of statistical software is going to spit out those 5 numbers. Used to be way back when that they were all referred to as quartiles, and in fact, a lot of times when we talk about Quartile 1 and Quartile 3, a couple of students will ask what happened to Quartile 2. Well, the median used to be Quartile 2. And there's still some older textbooks out there that refer to the median as Quartile 2. Now, this way of determining the quartiles, if you had an odd number of numbers, like we were talking about earlier, if you have an odd number of numbers, then you have one number which is in the center, and in this case, 4 numbers below it and 4 numbers above it. That number which is in the center is the median. That is not counted as part of the bottom half or part of the top half. So the median has separated the data into 2 halves. The bottom half is these 4 numbers, and we cut that in half, and that's Quartile 1. And the upper half is these 4 numbers, and we cut that in half, and that's Quartile 3. So this way that I've just demonstrated of determining the quartiles, this is exactly how most of your graphing calculators do it, and it's exactly the way the Excel spreadsheet function called quartile.exe works. That's how most of the planet determines quartiles. Quartiles, according to our book, are a little bit different. And for the most part, it matches up with what I just showed you. But because the problems on the homework and the quizzes are randomized, you need to know how to do it the book way as opposed to the calculator way, or the calculator might cause you to get a problem wrong on the homework. And this procedure is also important to know because it's similar to how the book finds the percentiles, which is coming up in a little bit. So to find the locations L for the quartiles. Multiply the number of numbers by 0.25 for quartile 1, because 1/4 of the data is below quartile 1, and 0.75 for quartile 3, because 75% of the data is below quartile 3. Here's where it gets a little bit weird. If the answer you get for L is a whole number, then you're going to take the average of the numbers in position L and position L plus 1. If L's not a whole number, then you're going to round L up, not round it off, but always round it up to the next whole number and use the number in location L after rounding up. So I know that sounds very complicated. Let me demonstrate that 4 different times. So first of all, I'm going to compare the book procedure with the TI-84 procedure. First of all, I'm going to compare them for a data set that has 8 numbers. I'm looking at a set of numbers. I'm looking at a set of numbers that is a multiple of 4, because if the number of numbers is a multiple of 4, then it's easy to split it up into 4 pieces, and both methods arrive at the same answer. So the TI-84 procedure I told you was find the number in the middle, which is in between the 4th number and the 5th number, x subscript 4 and x subscript 5. And then you have 4 numbers on the bottom and 4 numbers on the top. The center of those 4 numbers on the bottom is here. The center of those 4 numbers on the top is here. Again, add 2 numbers together and divide by 2. So the book procedure says you find L by doing 0.25 times n. So 0.25 times 8, the number of numbers in our data set, is 2. And the book procedure says when this turns out to be a whole number, you do the average of the numbers at position 2 and position 3, which is exactly what this calculation here is. And then for quartile 3, you find L by doing 25% of the number of numbers, so 75%, excuse me. So 75% of 8 is 6, and when this comes out to be a whole number, then we average the numbers at position 6 and position 7. So average them means add them up and divide by 2. So that's exactly the same the way the calculator would do it. So what if we had a number of numbers that was a multiple of 4 plus 1, like say 9 numbers? So now I'm referring to the numbers as x subscript 1 through x subscript 9. So as I showed you earlier, that means item number 5 or location number 5 will be in the center with 4 numbers above it and 4 numbers below it. And for the 4 numbers below it, you find the center right there by adding 2 and 3 together. And for the 4 numbers above, you find the center right here by adding 7 and 8 together. So this is the calculator way of doing it. Here's the book way of doing it. For quartile 1, find L by doing 0.25 times 9, since we have 9 numbers. And 0.25 times 9 is 2.25, which is always supposed to get rounded up. So we round up to 3, and we simply use the number at location 3. For quartile 3, you find L by doing 0.75 times 9, which is 6.75. You round that up to 7 and use the number at location 7. Notice that this is as if they're including the median in the bottom half and saying those 5 numbers has x3 in the middle, okay? And it's the same as saying we're including the median in the upper half, and those 5 numbers have x7 in the middle. That seems like kind of what they're doing, but you'll see in a moment that that's not always what they're doing. So again, it's a little bit different the way the book does it. If the number of numbers in the data set was a multiple of 4 plus 2, like say 10, which is 8 plus 2, then the 2 methods are in agreement. So here's our numbers from x1 through x10. The calculator way of doing it is to find the number in between x5 and x6 by adding them together, divide by 2. That leaves you 5 numbers in the bottom half and 5 numbers in the upper half. And the 5 numbers in the bottom half have x3 exactly in the middle, and the 5 numbers in the upper half have x8 exactly in the middle. To follow the book routine, you find the location for quartile 1 by doing 0.25 times the number of numbers. And 0.25 times 10 is 2.5, which rounds up to 3, so you use the number at location 3, same as what we have down here. You find the location of the third quartile by doing 0.75 times the number of numbers, which is 7.5, which gets rounded off to 8, so you use the number at location 8. So in this case, the book method and the TI-84 method come out to be exactly the same. The last one we should look at is if the number of numbers is a multiple of 4 plus 3, like say 11, because 11 is 8 plus 3. If we go one more, we'll be at 12, and we would be at a multiple of 4 again. So a multiple of 4 plus 3, like 8 plus 3 is 11. So now we've got the 11 numbers lined up. The TI-84 method is the median is x6 because that has 5 numbers below it and 5 numbers above it. And then now you forget about the median and you look at the 5 numbers in the bottom half. x3 is in the middle of that. And then you look at the 5 numbers in the upper half, and x9 is in the middle of that. So that's pretty straightforward the way the calculator does it. The way the book does it, median is the same. And then here's how we find quartile 1. Quartile 1, the location is 0.25 times 11, which is 2.75, which rounds up to 3. So you use the number at location 3. Quartile 3 location is 0.75 times 11, which is 8.25, which always has to get rounded up. So we round up to 9, use the number at location 9. So the only time they're in disagreement is this situation right here, where the number of numbers is a multiple of 4 plus 1. So like 8 plus 1 would be 9, or 12 plus 1 would be 13, or 16 plus 1 would be 17. So if you have a number of numbers that's a multiple of 4 plus 1, the book method and the calculator method will give you slightly different answers. So just be aware of that, because if you just punch the numbers into your calculator, it might not give you answers that will be marked correct on a homework. Okay, so that's the wonderful world of quartiles. There are other types of aisles. For example, there's quintiles, which instead of dividing the data into 4 pieces, divide it into 5 pieces. And back in the day with the state testing in California, those 5 pieces used to be called far below basic, basic, proficient, and advanced. There's also some data sets that get split up into 10 pieces, which is deciles. And then the final aisle is that there's something called percentiles, which is an attempt to divide the data up into 100 pieces. So here's the way we establish percentiles. So in general, a number is said to be at the pth percentile if p% of the data lies below that number. Okay, so there's not perfect agreement on how to do this, kind of similar to the quartiles. Some books say it's the percent of data below a certain number. Other books say it's the percent of data at or below a certain number, meaning they're including ties. But I think the most common usage is to say that if you have a number at the 90th percentile, 90% of the data is below that number. So for example, if your height is at the 90th percentile, then that would mean that 90% of people are shorter than you. Or if your quiz score is at the 90th percentile, then that means 90% of all quiz scores are less than yours. That's the most common usage of the term percentile. So here's how the book calculates this. If you want to find the pth percentile, you do p divided by 100 and then multiply by the number of numbers in the data set. And that will give you L, the location of the pth percentile. Now, similar to what we saw with quartiles, if L is a whole number, then we're going to average the values found in position L and position L plus 1. But if L is not a whole number, then we're going to round up and use the number in this new position L after the rounding. So in our data set, if you want to find the number at the 15th percentile, you do 15 divided by 100. You multiply that by 8 because we have 8 numbers in the data set. So the location we're looking for is location 1.2. Now, I will interject this right here. The number 10 is at location 1, and the number 11 is at location 2. And some software packages do some interesting calculations to figure out where in between there would be location 1.2. If this is location 1 and this is location 2, then somewhere in between would be location 1.2. There are methods of finding the percentiles that go to that length, but our book method does not do that. All they do is, if this don't come out even, round it up. So in this case, it rounds up to 2, and we use the number in location 2, which is the number 11 in our data set. So we say that 11 is at the 15th percentile. Now, there's a problem with trying to take a set of only 8 numbers and split it up into 100 pieces. That leads to some weird things happening. For example, if I had asked instead of the 15th percentile, if I had asked for the 20th percentile, then we would do 20 divided by 100 and multiply by 8 and get position 1.6, which rounds up to 2. And the number in position 2 is again the 11. So we would say that the 20th percentile is 11. But we also said up here that the 15th percentile is 11. And so the problem with a really small data set is that we've got 25% of our data that is at or below 11, but we only have like 12% of our data that's below 11. So that can lead to some interesting answers, but I would say usually percentiles are used with really large amounts of data like test data, SAT and stuff like that, really big tests, and so you don't run into that issue. But I'm just saying that it's legit with this small data set to say that 11 is the 15th percentile and also say that it's the 20th percentile. Oftentimes we have to do this operation the other way around. For example, look at our numbers in our data set. What is the percentile or the percentile rank for the number 23 in our data set? Well, it depends if you just look at how much of the data is below 23, or if you look at how much of the data is at or below 23. So if you ask what percent of the data is below 23, there's 6 numbers less than 23, which is 75% of the data. So it's completely legit to say that 23 is at the 75th percentile because 75% of the data is below 23. However, other books would say there's 7 numbers that are at or below 23, including that tie at 23, and that would be 87 or 88% of the data is at or below 23. So that's the 87th or the 88th percentile. Usually this is rounded off to a whole number. Usually we wouldn't say the 87.5th percentile. And if this was a written test in a traditional classroom, I would accept either one of these answers or the 75th percent. Any of those answers I would accept. But the book has a method that will give us an answer in between those two. So the book wants you to do this. Look at the number of numbers that are less than x, x being the number that you're trying to find the percentile of. Add a half to that and divide by n and multiply by 100. So in our case, there's 6 numbers that are below 23. You add a half to the 6, and you divide by the number of numbers, which is 8, and you multiply by 100. This gives you 81.25. You round that off to the nearest whole number, 81. So we would say that the number 23 is at the 81st percentile. So that's it for percentiles. The final way of measuring position is something called z-scores, but we won't be able to talk about z-scores until after we've talked about standard deviation. So now we move on. So we've done measures of center, we've done measures of position or location, and now we're doing measures of spread or measures of variability. And there's a couple really simple ones and a couple that are more tricky. But in general, we're looking to have a number that tells us how far spread out the data is. A kind of elementary school number is the range, which is just the maximum minus the minimum. So in our data set, the range would be 29 because the maximum minus the minimum is 29. That's very simple. Another measure of spread is called the Interquartile Range, which is abbreviated IQR, and that's also pretty simple to calculate once you have the quartiles, because it's just the distance between quartile 3 and quartile 1. So remember the way we determined the quartiles earlier with our data set. This is how we found the quartiles earlier with our data set. So the IQR is simply 21 minus 11.5, or 9.5. So that's a really simple calculation, assuming you already have the quartiles. And now that we have the quartiles and the IQR, we can talk about outliers. So it's not cool to just say, hey, that number 39 is weird because it's way far away from the other numbers. There's a specific statistical terminology, which is called outlier, to describe unusual points, and the point has to meet certain calculations in order to be called an outlier. So the first thing you do is you calculate 2 outlier fences, and they're calculated in a similar way. The lower outlier fence is quartile 1 minus 1.5 times the IQR. Any number smaller than that will be an outlier. And then we have an upper fence, which is quartile 3 plus 1.5 times the IQR. Any number greater than that is an outlier. So for our data set, we had this 5-number summary, and then we calculated the IQR from the quartiles. So the lower fence is quartile 1 minus 1.5 times the IQR. That takes us to negative 2.75. There is no data in our data set that is less than negative 2.75. We don't have any data that's negative. For the upper outlier fence, we do quartile 3, which is 21, and then we add 1.5 times the IQR. That takes us up to 35.25. And we do have one number in our data set that's greater than 35.25. So we say that 39 is an outlier because 39 is greater than 35.25. Very important that you make this comparison here, because anybody could look at this data set and they could just take a guess and say, hey, 39 is an outlier because it's the biggest number. But that's not a mathematical justification. If you're going to call 39 an outlier, then ideally I would like to see a calculation of both outlier fences, and then I would like to see you comparing the number 39 to the fences in order to justify that it's an outlier. And similarly, if you're going to claim that there's no outliers, then you should also make that claim by saying all of the data is between the fences. So also with the 5-number summary, we can do something called a box plot. A box plot is basically just a graph of the 5-number summary. The hardest thing when we're doing this on paper, the hardest thing for students, it usually is to get a well-spaced out number line. But once you have a well-spaced out number line, you just put a dot for each number in the 5-number summary. So you'll see here I just have 5 dots, and then a box or a rectangle around the quartiles with a vertical bar at the median, and then a whisker from quartile 1 down to the minimum, and a whisker from quartile 3 up to the maximum. And notice also that I have labels for each of these points, not only labeling that this is the minimum, but specifying that that's 10, and labeling that this is quartile 1, and that's at location 11.5, and so on. So that labeling ideally should be a part of it. So this is how a box plot looks in Desmos. Here's how that same box plot looks on our graphing calculator. The only thing that kind of sucks a little bit about the graphing calculator is that there's no numbers here on the x-axis. So unless we press a couple more buttons on the calculator, we don't really know what these locations are. And also, we talked about outliers just a little bit ago. Sometimes box plots are modified in such a way as to display outliers. And in fact, a box plot like that is literally referred to as a modified box plot or a modified box and whisker plot. So if you look at these two from our TI graphing calculator, down here, they're exactly the same. The only difference is in this one, the number 39 has been identified by some kind of special point. Sometimes it's a little circle, sometimes it's an asterisk or whatever. And sometimes you have data sets with more than one outlier. For example, if I go back to this Dodger data, if I change my graph from a histogram to a box and whisker plot, there's at least 1, 2, 3 points here identified as outliers. So sometimes you don't have any outliers, sometimes you just have one, sometimes you could have many. Also, while I'm here, a kind of an unusual feature of this box plot is you notice there's no whisker over here. And the reason why there's no whisker over here is the data at the bottom end is so tightly bunched that quartile 1 and the minimum are actually the same number. So when you draw the whisker from quartile 1 to the minimum, there's no whisker to draw because you have so many people tied with that lowest score, that lowest score, or in this case, the lowest salary, is both the minimum and quartile 1. So anyways, that's a modified box and whisker plot, which is a really common way of displaying data. And also, box plots are an easy way to compare data because you could easily put a box plot up here with a different set of data, and then you can just directly compare them side by side. Anyways, not only is the 39 identified as an outlier, but this whisker does not go, many people think that the whisker is drawn to this number here, 35.25, which is our upper outlier fence. But no, the whisker is drawn to the biggest number in the data set that's not an outlier. And for our data, that would be the number 23. The number 23 is the biggest number that's not an outlier. So that's where the whisker is drawn to. So that's box plot and modified box plot. And I think on the homework, you just have little sliders down here that you just slide the maximum to the right spot and you slide quartile 3 to the right spot. So there's not even anything to type, I don't think, when we do this on the homework. Okay, so the final sort of discussion is another measure of spread, which is really widely used a lot in this class later on especially, and that's standard deviation and variance, which kind of go hand in hand, as you'll see in a second. So we want to try to figure out, on average, how far is the data from the mean. So remember, range was a measure of spread, and that was just the distance from the minimum to the maximum. IQR, or interquartile range, was a measure of spread, and that was just the distance between the quartiles, quartile 3 minus quartile 1. But this is looking at it a different way. We want to know how far, on average, is the data from the mean. So I've organized this in a table. I've first listed all 8 numbers in our data set. And remember, way back when, see if I can scroll all the way up. Way back when, we had figured out that the mean for this set of numbers is 18. So if the mean is 18 and I want to know how far the data is away from the mean, I'm going to take every number in the data set and subtract the mean. So when I do 10 minus the mean, I get -8, which is indicating that 10 is 8 below the mean. And so I do that with every number and I find out how far it is away from the mean. These are referred to as the deviations from the mean, which is why the measure that we're leading up to, the measure of center that we're leading up to, is called the standard deviation. And we'll also see there's a reason why it's not called the average deviation, it's called standard deviation. And one reason why we can't find the average deviation, now that I have all these deviations, you could add those deviations together and divide by 8 to find the average deviation. But the problem is, if you add these deviations together, as I'm showing right here, it adds up to 0. And that's kind of a interesting property of the mean, is that the deviations from the mean will always add up to 0. So to prevent these negatives and positives from canceling out, we're going to square all those deviations. That's my next column. So 10 was 8 away from the mean, and now we're squaring that and it becomes 64. So now all of these squared deviations are positive, and we're going to add up the squared deviations, and that gives me 636. Divide that by the number of numbers, and you get the average squared deviation. So 636 divided by 8, and you get 79.5. So we've got the average, not the average deviation, but the average of the squared deviations by adding the squared deviations together and dividing by n. This number here, very important number, that's called the variance. And in a lot of higher level stats classes, they tend to talk about variance more so than standard deviation. So this number here is the variance. And if you put everything together into a formula with the proper symbol, population variance, which is lowercase Greek letter sigma squared. This Greek letter sigma kind of looks like a sideways 6. The sum of the squared deviations divided by n. That's variance. Okay, and before we get into how that gets tweaked into standard deviation, there's another version of this formula that some people like better. As a matter of fact, let me go to the formula sheet really quickly and see if both of them are on the formula sheet. So here's your formula sheet for chapter 3, and the formula I just hit you with, that's the formula right here for the population variance. So that's on the formula sheet. But a lot of textbooks show a slightly different formula, which is kind of interesting because it comes up with the same answer. So instead of the sum of the squared deviations divided by n, another formula that gives the exact same result is this: sum of the x squareds minus the sum of the x's squared. So that right there is a little bit goofy to some students because sum of the x squareds, sum of the x's squared sounds like you're talking about the same thing, but it's different. The sum of the x squareds is summing the squares of the values of our data. The sum of the x's is what the data adds up to, and then that sum gets squared. So here you're squaring the sum, here you're summing the squares. Anyways, the sum of the x's squared divided by n, and then that whole thing still divided by n. And when you sum the data squared, you get this. And when you square the sum and divide by 8, you get this. And lo and behold, when you subtract those two numbers, you get 636, which is exactly the same 636 we had up here. And so the final answer, 79.5, is the same answer we have down here. Also wanted to show you that most number crunching software, like our calculator, is of course going to spit out the mean, but it's also going to spit out the sum of the x's and the sum of the x squareds. So this is our data set. The mean is 18. We saw that earlier. The sum of the x's is 144, which is showing up right here in the formula. And the sum of the x squareds is 3228, which is the sum of all these right here. Okay, so whichever formula you use, we're getting 79.5 for the variance. Okay, now usually you don't have to do this by hand because we have some kind of technology, whether that be a calculator or Microsoft Excel or whatever. But the point is, that's how you do it if we were doing it by hand. And then once you have the variance, you simply take the square root and you get the standard deviation. So notice now it's just sigma instead of sigma squared because I've taken the square root. And now this is the same formula we had before for variance wrapped up in a square root sign. And this is the secondary formula for variance that I was just demonstrating wrapped up in a square root sign. So the bottom line is the square root of the variance gives you the standard deviation sigma, which in this case is 8.916. And if I go back to my calculator printout, you'll notice here's sigma, 8.916. So like I said, usually we don't have to do this by hand, but it can come in handy sometimes to know how to do it by hand. So those are the formulas for population variance and population standard deviation. Now, these formulas get changed in a few key ways if we're talking about a sample. So first of all, the sigma, instead of a Greek letter, becomes a regular letter S if we're talking about a sample. S squared if it's the sample variance. That's the first change. Second change, instead of mu, instead of subtracting mu, the population mean, we're subtracting x bar, the sample mean. Third difference, instead of dividing by capital N, which is the population size, we're dividing by lowercase n, which is the sample size. And then the weirdest difference is, for some reason, when we do the population standard deviation and variance, we divide by n. When we do the sample standard deviation and variance, we divide by n minus 1. Other than that, the formulas are identical. It's the sum of the x squareds minus the sum of the x's squared. That one is divided by n still, but the whole thing divided by n minus 1. So if I can show you really quickly on the calculator, remember this 144 and 3228. If I do 3228, which is the sum of the x squareds, minus the sum of the x's, which is 144, squared, divided by n, and divided by n, that gives us that number, which I would really like to see as a decimal. Unfortunately, I entered this fraction, so it made it a fraction. There's our 79.5 from before. And then I take the square root of that answer. And there's our 8.916 that we had up here. Okay. Now, all I have to change is the very bottom denominator. If that very bottom number gets changed to a 7, n minus 1, and everything else stays the same, that gives me this, which I would like to know as a decimal. That's 90.857, which you see right here. And then if I take the square root of that answer, that's 9.53, which you see right here. Okay, and on top of all that, the calculator, when you do one variable statistics, the calculator does not know if the number you're entering represents a sample or a population. So the calculator spits out S, 9.53, and it spits out sigma, 8.91. Just so that you're covered either way. It gives you both the standard deviation of the sample or standard deviation of the population, because it doesn't know if the data you entered was a sample or a population. It doesn't give you the variance, but it's pretty easy to find the variance. This S and sigma are both stored on the calculator. So if I take the S for standard deviation and I square it, there's the 90.857 from here, so there's the variance. If I take the sigma and I square it, there's the 79.5 that we had up here earlier. Okay, but usually in this class, we're going to be talking in terms of standard deviation and not variance. Sometimes in an engineering class or something like that, they'll talk about variance more so than standard deviation. There's a lot of other interesting things we could talk about with regard to this calculation for variance and standard deviation, but the main one I wanted to talk about is this. If you subtract a constant from every number in the data set, it does not change the spread. So for example, here's this data set that we've been working with. Suppose we subtract 10 from each number, which results in this. Notice the spread, 29 minus 0, the maximum minus the minimum, is still 29. In other words, the range is still 29, which we found for the range way up here. So subtracting 10 from every number made all of the numbers smaller, but it did not change how far spread out the numbers were. Now notice, if I subtract 10 from every number, that does change the mean. Surprise, surprise, it changes the mean by 10. The mean was 18 and now it's only 8. But if we look at the variance, if I square all the numbers in the data set and add them together, and then I subtract the sum of the data, squared divided by 8 divided by 7, I'm right back to 90.857, which is our variance. So the variance as a measure of spread, and also the range as a measure of spread, does not change when you subtract something from each number, or for that matter, if you add something from each number, because the numbers are either moving down the number line or they're moving up the number line in unison. So the biggest number and the smallest number, they're both moving the same amount in the same direction, so the spread doesn't change. That's kind of an interesting thing about standard deviation and IQR and range and all that. Also, returning to something we were talking about earlier, that we were talking about you should use the median as a measure of center when the data is skewed. So just to add on to that a little bit, if you're using the median to measure center, then you should use the IQR to measure the spread. Median and IQR kind of go hand in hand. If you're using the mean to measure the center, then you should use standard deviation to measure the spread. They go hand in hand. So again, if the distribution of data is symmetric, which it will be very often later in this class, then you use the mean for the center and the standard deviation for spread. But if it's skewed or it contains outliers, then you use the median for center and the IQR for spread. And now that we've talked about standard deviation, we can talk about one more measure of location or measure of position, which is the z-score, or sometimes called a standardized score. So here's an example. Suppose you have the average height of all adult males in the US is 69 inches with a standard deviation of 3 inches. And the average height of all adult females in the US is 65 inches with a standard deviation of 2.5 inches. I like using those data sets quite a bit. We're going to see that in another chapter a lot. Suppose we have a man who's 73 inches tall. That's clearly above the average of 69. And we have a woman who's 68.5 inches tall, which is clearly above the average of 65 inches for women. Both of them are above average, but which one is taller with respect to others in their gender? So we're going to compare those using z-scores and using this formula here. The number in our data set minus the mean of our data set divided by the standard deviation of our data set. And this formula is also on the formula sheet right here. Okay. So x minus mu tells us how far the data is above the mean, but this is really key. When you take that quantity, x minus the mean, and you divide by sigma, now you're measuring how far you are away from the mean in standard deviation units. And because it's in standard deviation units, that's why it's sometimes called a standardized score. So for our male, we take our male height of 73, subtract the mean of all males, and divide by the standard deviation of all males. So the 73 minus 69 tells us that this male is 4 inches above average height. But then we do that 4 divided by the standard deviation of 3. And this number here, 1.33, that's this male's z-score, which means that this male is 1.33 standard deviations above the mean. Okay? Do the same thing for the female. Her height of 68.5 minus the mean of all females divided by the standard deviation of all females. So she's 3.5 standard deviations above, sorry, 3.5 inches above the mean. When you divide that by the standard deviation, we get that she's 1.4 standard deviations above the mean. So the female is actually taller relative to those in her gender than the male is, because she is more standard deviations above the mean than the male is. And so just like I did here, z-scores are often a great way to compare two numbers from two different data sets, even when those two different data sets are measured on different numerical scales. For example, you could compare someone's ACT score to someone's SAT score, which you'll see on the homework. And all you need to do is you need to turn someone's ACT score into a z-score. By the way, this whole topic is called z-scores because it came from the field of education and talking about test scores. You can also do a problem like this, I guess you could say backwards. How tall is an adult male if we know his z-score is 2.1? So now I'm using that same z-score formula from before, except now I know the z-score is 2.1. I still know average male height is 69, and I still know the standard deviation of male heights is 3. I just don't know this particular male's height, which is x. So multiply both sides by 3, and you get this. Add 69 to both sides, and you get this. So a man's height is 75.3 inches if he has a z-score of 2.1. So that's a little bit of algebra, I guess, that you have to do there. Here's a similar question. How tall is a female whose height has a z-score of negative 0.7? So again, you put that in the z-score formula where the z-score goes. The mean female height, the standard deviation of female heights, solve this algebraically, and you find that if a female has a z-score of negative 0.7, then her height is 63.25 inches. And for those of you that might be algebraically challenged, here is the z-score formula solved for x, because this procedure that I did here comes up often enough that you might want to have this version of the formula on your formula sheet somewhere next to the z-score formula with that solved for x. So that wraps up Chapter 3 and all of our numerical summaries of data. You should be ready to tackle the Chapter 3 homework.